Hello friends, today I will discuss about the principle of the organic photodetector, how the organic photodetector will work, how we have to design the organic photodetector for efficient generation of the photocurrent, right? The principle of the organic photodetector. So, for organic photodetector, we have to create two different kind of the structures, right? One is the vertical structure, and another is the lateral structure. Vertical structure means we will have the active layer here, and here we will have two metallic layer. This is anode, and this is cathode. This is like a lateral structure, and another is the vertical structure. In this vertical structure, all the layers should be deposited over the other layers, right? Like in a stack. Okay, this is the vertical structure. Suppose here anode or active layer. These are the active layer, and here is the cathode. Okay, so you can design two different kind of the structure, but for case of the vertical layer, so this will be more preferable over the active layer. So if you want to know the vertical transport, if you have, and if you are using any kind of the material which have the vertical carrier, high vertical carrier mobility, for this kind of the material you have to choose the vertical transport, right? Apart from this, so in this case, here what is happening, in this case the light will directly fall into the active layer, but in this case the light will be transferred through the anode and into the active layer. Okay, so proper absorption will not take place in this case, but in this case the active layer directly absorb the light. Apart from this thing, if you want to think about the transport, charge transport, so this is more efficient over this thing. Okay, suppose if anywhere electron hole pairs are generated, so it will take lots of time to dissociate. Okay, but in this case, that will be efficient more. It's if we electron hole pairs are generated into this active layer, it can be efficiently transported into the anode and cathode layer. So overall, we have to choose the vertical layer as compared to the lateral structure. This is about the structure. Right. Now I come to the main layers. How many layers are required mainly? Okay. So I am considering the vertical structure. In this vertical structure, okay. So this is like a structure of the organic photodetector. So four layers. This is the basic structure. Four layers are there. This is the basic anode layer that you can use as a indium tin oxide. Why it will be used, that I will discuss later. After that, above the anode, we have to deposit one p-type layer, and then one n-type layer, organic semiconductor, and after that aluminum. P-type semiconductor, n-type organic semiconductor, and aluminum. So you have to connect the reverse bias in between anode and cathode, and light will be fall into the device through the ITO layer. So this should be transparent. Okay, so one p-type layer and one n-type layer, this should be sandwiched between anode and the cathode. Okay, after that you have to apply the reverse bias. Okay, so how we will choose the p-type and n-type material, this I will tell now. Before that, so the working principle of the organic photodetector, this is little bit different from the inorganic photodetector. But overall, the main photoelectric effect is the main base phenomena. Okay, but it follows some procedures. First procedure, if you want to generate a photocurrent into the external circuit. First procedure is the absorption of photon. Okay. Second is the generation of exciton. Third is the diffusion of exciton. Fourth is the this separation of exciton, collection of transfer or transportation of free carriers and collection by electrons. These 5 process steps we have to follow if you want to generate a photocurrent inside the organic photodetector, right? First, I will tell of this procedure. For absorption of photon, what is our requirement? Okay. So, as light is transferring through the ITO layer, absorption will take place in the p-type layer, because if it will take place in the n-type layer, so light has to penetrate into the device, it has to follow the multiple layers. So mainly the light will fall, absorption that is related with the p-type layer as compared to the n-type layer. So if the light will fall into this layer, that is the infrared structure, then this anti-material should be considered. Okay. So that means it is a metallic layer, right? So the light exciton will not take place in this layer. It will take place into the p-type layer. So what criteria should be matched to produce the exciton inside the p-type layer? Okay. So for that, suppose this is a p-type semiconductor. Means you have to use the p-type organic semiconductor, right? So what will happen? Okay. So this is the band gap, right? Band gap. Eg is the energetic difference between HOMO and LOMO of the p-type semiconductor, right? So there is a relationship between, all of you know, Eg is equal to 1240 by lambda, where and lambda is the nanometer. Okay. So this should be less than or equal to this energy. So if we apply X energy more than this Eg, this band gap, that time the electron will transfer from this HOMO level to LOMO level. Electron will transfer from HOMO level to LOMO level. Here a hole will create, here electron. This is called the exciton. Okay. So for that we have to choose such material, okay, so which follows this relationship. The band gap, this energy should be less than or equal to 1240 by lambda, where lambda is my wavelength of the photon, okay, wavelength of the light, right? Okay. So if you want to use the red light, so by using the Eg is equal to 1.24 by red light wavelength is 650 nanometer. Okay, so 1240. So from that you can calculate the band gap of the p-type semiconductor, right? So this is to choose according to our detector. What kind of the detector you want to design? Red light detector or visible light detector, or infrared light detector, UV light detector. Now I will come to the band diagram. Okay, so for discussing the other procedure, I have to discuss about first the band diagram. Band diagram should be like this way. So I will tell why the band diagram should be like this way. This is the p-type, n-type semiconductor, anode, this is the cathode. Okay. Now, so first step is the absorption. So if that condition is matched, that Eg is equal to 1.1240 by lambda, then electron will fall from this, electron will transfer from here to here. Okay. Then the electron hole pair will generate. Okay. This electron hole pair will generate. Now, what kind of the exciton will form inside the organic semiconductor? Frankel exciton. What is this? Actually, in case of the organic semiconductor, okay, all the free carriers are more localized into a single molecule, okay, and this is due to the low mobility. This is due to the low dielectric effect and low permeability. So all the free carriers are strongly localized into the single molecule. They are not localized, right? So due to this thing, the electron hole pair, this is strongly bounded, okay, with each other due to the Coulombic force as low dielectric constant, okay. So this is strongly bounded. So that kind of the exciton is the Frankel exciton that is generated in the organic semiconductor due to the structure of the organic semiconductor. After that, electron has to diffuse and it has to transfer at the interface. Why? Because this electron hole pair, this is bounded, okay. So normally the binding energy is the 0.4 electron volt, okay. To break this exciton, I need the high internal field, electric field, that is 10 to the power 5 volt per centimeter. Such amount of the electric field is required into the to break the exciton, okay. So if we will not use this n-type semiconductor, if we only use the p-type semiconductor, so such amount of the electric field will not generate inside the p-type semiconductor, okay. P-type semiconductor to break the exciton, okay. So to break the exciton, I need another n-type semiconductor, okay, to break the exciton. So what kind of the energy level should be there to break the exciton or to break the energy, to break this energy, okay. So this is called LUMO 1, I suppose. This is LUMO 2 and this is HOMO 1, HOMO 2, right? So we need some electric field to break the exciton, right? How we will get? At the interface, due to the energetic difference. Suppose this is this LUMO 1 minus LUMO 2. Here we will get some, if the LUMO of the p-type semiconductor is lower than the LUMO of the n-type semiconductor, some energetic gap is there. Okay, here also energetic gap is there, right? If there is some energetic difference between this LUMO and this LUMO, so we will get some difference, energetic difference, right? This electric field, due to this electric field, the exciton should be breakdown. For that, it has to diffuse into the interface, right? So, but the exciton has to diffuse at the interface within its lifetime, okay. Within its lifetime means, so the hole is produced here. So every exciton has some lifetimes, right? So if it will not break, if it will not generate a free carrier, to generate the free carrier, it should be break, right? If it will not break by the electric field, again the electron will be fall down into the HOMO level, okay. That means it will recombine again. So it has to diffuse at the interface before its excitonic lifetime, okay. Diffusion life, this is also called the diffusion lifetime. Suppose or also called the diffusion length. Suppose the diffusion length of this exciton is the 20 nanometer, okay. So that means the thickness of this p-type layer, that should be less than 20 nanometer, because the exciton will produce anywhere, right? So this should be the thickness of the p-type, this should be less than 20 nanometer. So if it is 30 nanometer, okay, so before reaching at the interface, exciton will recombine again, so we will not get any free carriers, right? This is the one condition, right? So this thickness should be, we have to design the thickness of the p-type in such a way that it should be less than the exciton diffusion length. Or we can create a multiple interface by mixing the p-type and n-type layer. By mixing the p-type and n-type layer. Okay, so everywhere it will get see some interfaces in p-type and in between p-type and n-type. So in between each and every interfaces, there will be only 1 nanometer and the 2 nanometer, right? Now, so So this is about the acetone diffusion. Now come to the acetone. Suppose acetone is diffused towards the interface. So it will now reach at the, it is now reached at the interface. Okay. Now, because for dissociation, by getting electric field, it has to diffuse at the interface. For getting the electric field, it has to diffuse at the interface. So at interface, it will see some energetic barrier. That means, suppose it is binding energy 4 binding energy of the acetone is a 0.4 electron volt. The difference should be greater than 0.4 electron volt. That is, the difference should be 0.5. The difference should be 0.5 electron volt. If this difference is 0.5 electron volt, then this energy should be dissociate this electron and hole pairs, right? Then the electron will be transferred into the LOMO level of the antimaterial, and here it will remain here only. Okay, it will remain here only. If acetone is produced into the antimaterial, then it will again transfer at the interface. At that moment, to break the acetone, this energetic barrier should be considered. Then this energetic barrier should be greater than the acetone binding energy, so that the hole can transfer here. So that hole can transfer from here to here. Electron will be remain same here. Okay. So now the electron will reach into the p-type antimaterial LOMO level of the p-type material, and hole will be remain same here. Right? After that, so this, once it will collected by the electrodes, then you can get some photocurrent in the external circuit, right? So again, it can transfer. So due to the diffusion concentration gradient, it can automatically transfer into the cathode, and it can automatically transfer into the anode. But we need a fast process. So after generation of the acetone, immediately we should get the electron and hole pair at the electrode sides, right? To to getting the first collection. For obtaining the first collection, I have to apply the reverse bias. So reverse, negative bias here only, positive bias here only. Okay. Due to the negative bias, the hole will be collected very fast. If we apply the negative voltage more, the hole will be collected very fast, and electron will be collected by the cathode. Now, so the cathode should be extracted this electron. For that also, this energetic barrier should be very less. Energetic barrier between this LOMO level of the antimaterial and cathode should be very less. So we have to use aluminum, because the aluminum should be aluminum is normally matched with all the LOMO level of all the organic semiconductors, right? Okay, we can also use silver, but best is the aluminum. Aluminum normally, silver can normally, both can normally oxidize with the environment. So after the aluminum, we can also use the capping layer as a gold. This is the capping layer, okay, for less degradation. Okay, again the hole should be collected by the anode. Okay, for that this energetic barrier should be very less. So we have to use the ITO or gold, but ITO will be preferable because it is more transparent. Gold is not transparent. If light will fall into the gold, it will be photon will be absorbed by the gold. Okay, so better if we choose the ITO, right? So, and this ITO, the work function of the ITO, that is also matched with the HOMO level of the all type of the p-type semiconductors. Okay, so this is about the energy level diagram. So if this is matched with the LOMO level, it can easily collected by the electrode. But for faster transfer, we have to apply the positive bias here, and here will be collected by the ITO. And for faster transfer also, this negative bias you have to apply at the ITO side. So first is the acetone generation, second is diffusion, acetone separation. For acetone separation, these criteria should be matched. Okay, for diffusion, we have to check the diffusion length of the acetone, and accordingly we have to change the thickness, right? And this is the gap. This gap should be maintained such a way that so that it can break the exciton, right? Again, and this energetic there should be the less energetic gap between this cathode and the LUMO one and anode and the HOMO one. So after that, for efficient transport, I have to apply the reverse bias. Okay, but this should not be, this gap should not be, this gap, this LUMO 2 and the HOMO 1, this gap should not be less than zero point 0.3 electron volt. If it is less than 0.3 electron volt, again electron will be easily recombined by the hole, okay, into the, and there will be one tunneling phenomena. Okay, so this should not be less than 0.3 electron volt, right? So this is about the main principle of the organic photodetector. And for improvement of the performance, we have to also use, if this gap is more and this gap is more, we have to use the another interfacial layer. Because suppose I have chosen such kind of the organic semiconductors, it has other good properties, right? But this gap is more, okay, this gap is more also, this gap is more. So for that we have to use the interlayer between LUMO anti-semiconductor and cathode layer, and ITO and the p-type semiconductor. Okay, so I will discuss what kind of the material we can use for other additional layers, right? So this is about the principle of the organic photodetector. So next class I will discuss about the structure of the organic photodetector, like a bulk structure, mixed structure. Thank you.